12:03.
Okay. All right, good afternoon. Welcome to the last day of the press briefings at the 47th Annual DPS meeting. My name is Dr. Vishnu Reddy. I am the press officer for the DPS. Today we have a very exciting panel. First, on my right, we have Dr. Michael Skrutskie. He's from the University of Virginia. He's going to talk about LBT observations of Io's volcanoes. Then you have Dr. David Tholen from the University of Hawaii. He's going to talk about evidence for an impact event on an asteroid. Then you have Dr. Sonia Fornasier from the Paris Observatory, and she's going to talk about results from the Rosetta mission. Then we have Dr. Dennis Bodewitz from the University of Maryland College Park, and he's also going to talk about observations of Comet 67P from Rosetta. And finally, we have Dr. Frank Marchese from SETI Institute, and he's going to show some really cool images of an exoplanet from the Gemini telescope. With that, I'll call Michael to come and take over.
Thanks a lot. I will start with a warning that the science content in the end of this is not so rich, but everyone who has seen this says it's one of the coolest things they've seen in a long time. And this is about Europa occulting Io while we were observing it at 4.8 microns in the thermal infrared. You can see the team of investigators up there. I want to point out, first of all, that Al Conrad has been leading a coordinated effort with the Large Binocular Telescope to observe Io at intervals to monitor the volcanic activity, and in particular to use the powerful resolution of the LBT to resolve the Loci Patera on Io. Ashley Davies from the team is here and will actually answer any technical questions about volcanism, because I'm the instrumental guy on this team, but somehow I got the privilege of giving the talk. I want to give everyone a little context just to make sure everyone's on the same page. Io is the innermost of the 4 large Galilean satellites of Jupiter. It is the most volcanically active body in the solar system because of its slightly elliptical orbit that leads to tidal squashing over time. Further context, these observations happen in the mid-infrared at 4.8 microns, 10 times the wavelength of visible light. That's a wavelength where room temperature objects are slightly above room temperature low. That's my dog, hot eyes, cold nose. And what that's really telling you is this is a wavelength that's diagnostic of temperature. Basically, 2 things make something bright at these wavelengths. Either it's hot or it's large. And if it's hot and large, it's extremely bright. And on the upper right of this slide, you see a thermal infrared image of Io taken with the Large Binocular Telescope. One very bright volcanic region, warm and large in this case, which is Loci Patera that I'll be talking about. Large Binocular Telescope, the world's largest telescope at present. Largest collecting area, 2 8.4 meter mirrors. I might as well show you the nice breathtaking close-up view. You'll see a person right in the middle for scale. The net collecting area of those 2 8.4 meter mirrors is equivalent to an 11.8 meter telescope. But more importantly, if you can make those 2 mirrors work in tandem to a fraction of the wavelength of light, and we do, you effectively, at least in one dimension, have a 23 meter diameter telescope, a 23 meter collecting area, which makes it twice as big in some sense than Keck. In order to do that, there's this marvelous little green thing, which is called the Large Binocular Telescope Interferometer, which takes the light from the 2 sides. You can see the mirrors sitting off to either side of that beam combiner built by Phil Hinz at the University of Arizona. It essentially registers physically those 2 mirrors relative to one another by about 1/100th the width of a human hair, a few tens of nanometers, and holds that steady so that the light interferes from the 2 sides. And so when you do that, and I'm going to start with a little observational context from really the beginning of this epic of observing Io with the LBT. When you interfere those beams, first of all, you get this fairly funky point spread function, funky image from the telescope, which is Venetian blinds, a sine wave right-left across the typical blurry Gaussian image that you usually see, which is what sharpens up the resolution. So on the left is sort of a raw interferometric image of Io, and on the right is the deconvolved image, where you take advantage of your knowledge of interferometry and the point spread function to sharpen things up. And in fact, you'll see dozens of volcanic sites on Io when you do that, and you see the Loci Patera in particular, the bright red spot there is in fact resolved, that you see detail in the Loci Patera region. And again, this is context from a paper. We had a press release about this a long time ago that shows that there were 2 regions of emission in Loci Patera in 2013. That image is from December of 2013. And so today I want to tell you about another observation in this series where you see the same thing. And so this is an animation, but you see zipping into the field of view something that doesn't belong there. And that is the disk of the moon Europa. To some extent, this was unexpected, and so this is a classic photobomb at some level. It wasn't really unexpected. We understand orbital mechanics so well that to the fraction of a second, people know exactly when this is going to happen. But when the proposal was submitted to do this work, we were entirely focused on making the observations of the volcano, using the power of the baseline of the LBT to resolve the details of Loki. It turns out that with this event happening in the middle of the observations, and the observations are obviously shifted in time a little bit to take advantage of this and to see it, but the edge of Europa advancing, and because the LBT is so big and capable of collecting so much light, we could take an exposure every 1/8 of a second, 8 exposures per second, and that meant that the limb of Europa advanced by only 2 kilometers between exposures, covering up 2 kilometers after 2 kilometers after 2 kilometers of the regions that we were observing. That's to compare with the 100-kilometer resolution of the blurry point spread function of the LBT. So although the LBT is the most amazing capability at these wavelengths on the surface of the Earth right now, and we can resolve Loki at a low level, Loki Patera at a low level, this is about 40 times better. And so where were we looking? You saw 2 bright spots in this image and multiple other volcanoes. We're focusing on the very bright one, which is Loki Patera, and you'll see that up close in just a second. And then you can see, this is an overlay on the disk of Io as it was rotated at the time, another emission region, which is an area called Pelon Patera, which is just off of Pele in the lower right on the disk. Here are close-ups of each of those 2 regions. So you see the large lava lake, which is Loki, solidified for the most part over top. And so we're looking at regions where that lava crust has opened up and exposed warmer temperatures. And Pelon is an active region on Io that has been erupting many times in the last few years. If you saw Catherine DeClear's talk just a little while ago, she talked about the history of volcanism on Io. So what I want to show you is how you really can extract a lot more information than meets the eye with this event. And so this is just a little cartoon. I'll advance it of the advancing limb of Europa moving across Loki Patera. You see that horseshoe there. And so this goes from the very first instant we detected a drop in light to the last instant where it had completely disappeared. And you can see the direction in which the limb of Europa is moving. And by the way, Europa is dark. I don't remember if I said it before. Because it's made of ice, and ice does not, or at least the surface is covered with ice, and ice does not reflect light very efficiently at all at the wavelength where we're working. So you're actually seeing most of the disk of Io in reflected sunlight. You're seeing Europa as a shadow in some sense because it's not reflecting much sunlight at all at these wavelengths. To get a little technical then, this is the actual occultation curve. Over it, as I said, 8 images per second, 2.4 kilometer shift. And what you see is actually a lot of structure in this if you look carefully. I'll walk over here.